Hi, welcome back. Let's today extend the idea of Faraday's law to write it in a more general form, also known as Maxwell's third equation. Let's start with Faraday's law in its well-known form, where epsilon is the induced electromotive force. The integral of B dot dA is the magnetic flux through a surface S. B is the magnetic field and dA is the infinitesimal vector element of the surface. This tells us that the change in magnetic flux through a loop creates an EMF, which can drive a current if the loop is made of conductor. However, we now need to clarify the nature of EMF and connect it to the electric field. Let's first pause for a moment and think about the electromotive force, which is not a force, but a voltage or a measure of energy. The electromotive force, EMF, is a measure of the work done per unit charge as the charge moves around a closed loop. Although it has force in its name, EMF is not a force, it is an energy concept. It represents the energy supplied to move a charge along a path. Think of a charge moving in a conductor loop under the influence of an electric field. The electric field thus works on the charge, giving it energy to move. EMF quantifies this energy. The electric field E at any point exerts a force F on a charge Q. F equals to QE. The work done by the electric field and the charge Q as it moves over an infinitesimal displacement dl is dW is equals to FdL equals to QEdL. For a unit charge, Q equals to 1, the work done over the infinitesimal path is simply dW is equals to E dL. Thus, the electric field contributes directly to the work done along the path. Now, imagine moving the charge around a closed loop C. This total work per unit charge is obtained by summing the contributions of E dot dl over the entire loop. Mathematically, this is expressed as a line integral. Epsilon equals to the closed integral of E dot dl. This equation defines the EMF. It tells us that the EMF is the cumulative effect of the electric field along a closed path. Imagine walking along a winding path on uneven terrain. At every step, the slope of the ground is analogous to the electric field, determines how much effort you need to exert. The line integral sums up all the effort that you've put in across the entire path. Similarly, the electric field E at each point pushes the charge along the loop, and the line integral adds up all the contributions. Now, we connect this concept back to Faraday's law. The induced EMF arises due to a change in magnetic flux through the surface enclosed by the loop. Combining these ideas, Faraday's law becomes the closed integral of E dot dl is equals to minus the derivative with respect to time of the closed integral of B dot dA. This is the integral form of Faraday's law. This equation connects two fundamental phenomena. A time-varying magnetic field creates an electric field. The circulation of the electric field, the line integral around the closed loop, is proportional to the rate of change of the magnetic flux through the loop. But this expression is not yet in a general mathematical form. To proceed, we use a powerful mathematical tool, Stokes' theorem. Stokes' theorem relates the circulation of a vector field around a closed loop to the curl of the field over the surface it encloses. The closed integral of E dot dl is the integral of the rotational of B dot dA. Thus, substituting this into our equation of Faraday's law gives Because this equation holds for any arbitrary surface, the integrands must be equal. Thus, we arrive at the differential form of Faraday's law. The equation encapsulates the following physical idea. A time-varying magnetic field generates a curling electric field. Unlike the electrostatic electric field, which arises from charges and is curl-free, this electric field is rotational, meaning it loops around the regions of changing magnetic flux. This is Maxwell's third equation, and it emphasizes the intrinsic link between electric and magnetic fields in dynamic systems. So Faraday's law bridges the gap between electricity and magnetism by showing how a changing magnetic field induces an electric field. The integral form relates the circulation of the electric field to the rate of change of the magnetic flux. Using Stokes' theorem, we derive the differential form, which is a part of Maxwell's equations. This result is central to understanding electromagnetic waves, as the interplay between fields lies at the heart of wave propagation. Thank you for your attention. May science be with you.